Okay, this is my pleasure to introduce you James Kane. So James Kane is a professor of computer science at the University of Cape Town in South Africa. He received his BSc with honors and MSc degrees in computer science from Rhodes University. And in 2000, he obtained his PhD from the University of Cambridge. He is a former president of the African Computer Graphics Association, AFRIGRAPH, and a winner of the University of Cape Town Distinguished Teachers Award. So he's doing a lot of stuff in computer graphics, but also in visualization and virtual reality. And today he will present his work on virtual worlds, and it's called Authoring Digital Landscapes.
Thanks very much, Eric. I actually work a lot with the two Erics and Adrien. And when I said I was going to come and give a talk here in Lyon, the person I was speaking to said, you're going to Lyon to tell them what they do already, which they surely already know. But actually, there are some aspects of what I'm going to talk about that wasn't joint research with the group. And what I'm going to talk about is the authoring of digital landscapes. And I've chosen this title very carefully because digital landscapes is one thing, but actually designing interfaces for artists to create those digital landscapes imposes a whole extra layer on top of the process. So just a little bit, I know that you're very familiar with computer graphics. I know this is probably the largest computer graphics group in France, but just make sure that we all understand the context here. I'm going to define what a digital landscape is, why it's important, and some of the constraints on designing them. So it's essentially the bare underlying earthscape, which we usually represent as a height field. And that will represent the bare landscape. And on top of that, you want to put all sorts of extra detail. So typically this would be things like forests, trees, plants, ecosystems, any kind of decoration that would go over the bare landscape. And not just that, you're also interested in the skyscape. So the surrounding world, in essence, anything that contributes to a natural representation in digital form of the world is what we're interested in. So things like snow, plants, rivers, weather, and so on. And where does this have application? It has application in computer games, film, and also for training exercises in virtual reality. Sometimes the concern is to have it as a background element in those scenes. So there it's for aesthetic purposes to maybe create a mood for the environment. But sometimes the actual simulation is really important that it be accurate. So the example I'm thinking of is things like flight simulation. You really want to get the weather right for a flight simulator because it directly affects how you would control the aircraft in that particular case. Let's turn now to the typical workflow of an artist in designing a natural scene, and you'll realize why it's quite important that we develop tools that are useful for them. So the typical workflow is that you will have in a game or a film some kind of script or a game design document that the game designer has created for the environment. Once that's complete, and of course it's a living document, so it might change. It depends on the scale of the project. Obviously, as you proceed with these projects, the design gets locked down further and further. But once you've got something in place, usually the artists or the visual effects experts will go out and they'll gather materials for pre-visualization of the scene. This might mean, in the case of natural environments, actually visiting a real site and taking photographs and videos and samples and so on. And then the digital artists will actually create the scenery assets during the actual development cycle. And that will be the typical combination of geometry, texture, and animation. You might think that being a digital artist is a wonderful thing, and in many respects it is, but in some other respects, this is what it feels like. You are a slave in a galley, working 60 or 70-hour weeks, sometimes doing the same thing over and over. It's a very pressured environment. And that's because a lot of the tools are actually fairly low level. Creating something like this tree here, if you're a digital artist without extra tools, would mean designing geometry assets of about 500,000 vertices. And that could, if you were an expert, take about 20 hours just for one tree, one hero tree element in the scene. If you've got an entire forest, obviously it becomes an almost unmanageable thing. Of course, what they do is they tend to have very highly detailed assets for what are called hero trees, the ones that are really close to the camera and less detailed further away, but it's still really a big task. So our purpose here is to create tools that streamline that process. We want to basically unshackle the digital artists from their rowing oars and allow them to do this in a much more efficient way. Not just efficiency, but also retaining creative control. So whatever tools we design need to basically be focused on the artist as a creator. And what I like to do is identify 3 important goals which infiltrate all of our work in this particular domain, which is plausibility, controllability, and efficiency. And these all work together. And in fact, where you want to be is at this intersection of the Venn diagram. You want your tool to sit in this particular space here, where it is both plausible, controllable, and efficient. Because that's what a good authoring tool is. And it turns out to be quite easy to get 1 or even 2 of the 3, but very difficult to get an authoring tool that combines all of those 3 things. And I'll show you some examples where we've achieved these proportions to different extents, but not necessarily achieved everything. Let me look at those 3 goals, the trifecta, I call them. The first one is controllability. And generally, we can take existing authoring tools in this domain, and even outside of this domain, and classify them according to this continuum. On the far left-hand side is complete automation. You, as a designer of the natural environment, give very little input. You might, for example, give a random seed, and the entire world is created out of that. On the complete reverse side is complete control, where you design the scene by specifying vertex positions, which of course is kind of crazy if you've got 500,000 of these things. And in between are the more realistic different kinds of controls. So you might have parameter setting where you tune different noise parameters. You might take existing data and input it and try and create something that has the same feel to it. You might use an interface which has a metaphor of sketching, painting, or sculpting, which is, as you will see, what we really like. This is where traditional modeling fits, more towards the complete control side. So this is something like constructive solid geometry, all the tools you will get in Blender, 3D Studio Max, and the typical modeling packages. And what I like to do is to divide this into 3 zones, let's call it. So zone 1 is if you're a designer and you're lazy. That's the lazy spot. Because you don't have to do a lot of work, but at the same time, you don't have a lot of control. On the other side is the sweat spot. So lots of work for the artist, rowing on the galley of the pain of spending 70 hours a week working. And then the place that we like is the sweet spot, which is a nice balance between automation and control. A few things to say about this. Even within this balance of automation and control, you still want to have further ways of specifying the level of detail. So sometimes what an artist wants to do is to say, I'm really concerned about this castle on the hill. I want to model the structure of the mountain in a lot of detail, but the plains around it, the plains of Mordor or whatever, it doesn't matter. They can just be normal plains gently rolling. So sometimes what you want to do is you want to have this within the same tool, gradations of control. So you should design for that because the artists sometimes want to be very specific, at other times they want to be quite general. So variable scale and precision within this sweet spot. And I really like to take the tools that artists have in the real world and try and translate them into the digital world. Of course, they change during that translation. So a pen in the real world, a pen or pencil in the real world is actually quite different from a sketching tool in a digital world, but there's still that inspiration. Okay, so that's the one thing, controllability. Let me talk a little bit about efficiency. And as with all computer graphics, we can divide it into different categories. And it's actually really important, the difference between these categories in terms of authoring. So real time for us, I think, is less than 0.1 of a second. So 10 frames per second or better. I would define interactive as anywhere from 10 frames per second to 5 seconds per frame. 5 seconds to 30 seconds, you can almost go away and have coffee, which isn't great for an artist. And nap time is anything more than 30 seconds. Why is this important? It's important because of the feedback cycle. So the artist makes a change, that change is realized in the authoring interface, and they see what the effect of the change is, and they can make further changes. The more you shorten that feedback cycle, the better it is as an authoring tool. And ideally, what you want to do is have a change and an immediate response to it. And that's this part here. So what you were seeing on the right-hand side, in fact, you can still see it, is a real-time system in terms of response. And if somebody doesn't like, for example, this border here, as they're painting it, they can adjust on the fly. So let me make this a little bit more clear. I'll give you another example. This is the difference between interactive and real-time. And I must apologize upfront to Eric for doing this. The system on the left-hand side is an example of an interactive system. So you can see what the author does is they paint a sketch, a section, and then a mountain is created from that. But there's a pause between when the artist completes the stroke and when the response of the system comes in. And that's, I think, about a second or 2 seconds, maybe. Yeah, approximately. Okay, so that's in the interactive timeline, and it changes the nature of the authoring system. You have to wait until you've completed the stroke in order to initiate the change to the landscape. Whereas on the right-hand side is an earlier system. I think it was animated earlier. Let me see if I can get it to play again quickly. That shows what happens if you actually, okay, speak to me, that's it, yeah. So here you can see as you're adjusting the height of the curve, there's actually a change in the landscape. So it's a real-time system. The reason why I say this is a little bit unfair is I think this is probably 256 by 256 height field, and this is probably 1024 by 1024 or more. So it's not really a fair comparison. And in many respects, this actually is the better system because it has a whole lot of other features. It's a very recent paper in which I was involved, but Eric is the first author, and it appeared at Eurographics this year. This is restricted. You can only use the tools that exist within the system. This one can import all sorts of terrain rendering and authoring tools from other systems into it. So the only respect in which this one is better is that it's actually a real-time system, and that one's interactive. That's why I said it was a bit of an unfair comparison, but I'm just using it for the purposes of illustration of the importance of efficiency in designing your authoring tools. Okay, and then the final one is the notion of plausibility. And sometimes people call this realism, but actually realism is too high a bar. We're not interested in realism for its own sake in computer graphics. What we're interested in is whether human beings can tell whether it's realistic or not. So if we can fool the eye, we can fool the viewer into thinking that it's real, then we're satisfied. And this turns out to be much easier to do than the bar that botanists, for example, set on ecosystems. They want their ecosystem simulations to be extremely realistic and based on nature, whereas all we want is to have it good enough that it looks real to the viewer. So this is why I talk about believability or plausibility and not realism. And that makes our task a lot easier as it happens. So how do you evaluate this plausibility as opposed to realism? Well, of course, we're in computer graphics, so we do the standard proof by demonstration, pretty pictures, but we don't just do that. So we can borrow something from the geomorphologists and the botanists. So we can look at validating it according to their measures. And we do some of that, but we don't go as far as they do. So the emergent physical properties of whatever system we create should be checked as well, if we can. And then the big thing is to do user experiments. And it's really only come in fairly recently in the field. And I think it's a really good move that natural phenomena have started to do much more of this in terms of experimentation. There's a bit of a caveat here. The caveat is that what you don't actually want is normal people in your user experiments. In particular, you don't actually want game players, because what's happened there is they spent a lot of time playing games. They're used to the depictions of natural environments in games, which are not real. And so they'll grade or compare on that basis. What you want is experts in the real natural phenomena. So people who go hiking, for example, are great candidates for these user experiments, because they'll do a comparison, a perceptual comparison with the real world, as opposed to what they've seen when they're locked in the basement with the game. Okay, so that's a bit of a caveat. How do we do this properly? How do we do this measuring of plausibility? We'd like to set up a proper perceptual user experiment. So that means having lots of people run through the experiment. And the ideal model for me is a two alternative forced choice experiment. So if you're comparing different representations, you put them side by side and you say to the viewer, choose A or B. You have to choose A or B. And you do this for a whole lot of different comparisons. And in the end, you run it through a standard statistical measure, the Bradley-Terry model. And incidentally, this comes from sports. So in sports, if you have a league of teams, you basically have a lot of forced choice experiments. You have team A, the South African rugby team, plays the French national rugby team. The South African rugby team beats the French national rugby team, of course. That's one experiment. That's a forced choice experiment. The French rugby team plays the English rugby team and they beat them. That's another experiment. Okay. And you get a whole lot of these together, and then eventually you can do a comparison of the different teams. And of course, with sports betting, they're really interested in these comparisons. But we can take that and we can apply it to our different methods of representing natural environments. And this is taken from Oscar Arguido's fairly recent work. And what he did is he did a representation of landscapes using aerometry, which is a technique from geomorphology for measuring the spacing and nature of mountain peaks. And then he performed a Bradley-Terry analysis on it. And it's really nice because you can see visually and statistically with significance what is better and worse. So for example, this here on the far left is a gradient constrained noise model. It's kind of fairly archaic, dating back 15 or 20 years. It does really badly in comparison. And you can even see the statistical significant difference because this part here doesn't overlap with any of the others. And that's an indicator, a visual indicator of that statistical significance. Whereas on the far right-hand side, you have data taken from the real environment. And that is statistically significantly different from the next best, but that's kind of getting close to the sort of thing we're looking for. So this is a real measure of plausibility, but it takes time and effort to do. You have to set up the environment to do the two alternative forced choice. You have to run it through at least 60, better yet more than 60 participants. You have to do the analysis. But I'd really like to see people in the natural phenomena domain turning to this on a more regular basis, because it is actually a good measure of whether something is plausible. Otherwise, all we're relying on is the pretty pictures. which we shouldn't just do. Okay. Right, so that is an idea of what it is we're trying to achieve. Now what I'm going to turn to is the general techniques for achieving it. And after that, I will look at some examples from my own work in collaboration with the two Erics and Adrian. Okay, so within computer graphics, there's really three approaches. And what's really nice is to mix them. So you essentially apply the right tool to the right part of your pipeline, and you get an effective authoring tool as a result. And we do that quite a lot. So the three general approaches, it's not that visible on this here, but three general approaches are simulation. So if you're creating, for example, a landscape, erosion simulation might be one way of doing that. The other method is the old standby of procedural approach. So think noise functions like Perlin noise, that's procedural. And the third one is the much more modern one of a data-driven approach. So that would be to apply machine learning as a technique. No one of those works for the three things I'm looking for, the trifecta of plausibility, efficiency, and controllability. So procedural methods are blindingly fast, well, assuming you choose the right algorithm. So they really win on the efficiency side of things. And you can also build in controls. So as you design the procedural algorithm, you build in a control for it. So you get these two things, but you do not get plausibility, even with pretty good algorithmic methods. So you can see on the right-hand side, at first glance, this looks pretty decent, but it has some real flaws from a geomorphological perspective. If you look here, for example, that central section, that actually is what is called an endorheic basin. It means that if you were to dump water onto this landscape, it would just basically fill up here and not flow off. And it's reasonably rare to encounter these in a real environment. Like, okay, Salt Lake City, yeah, that has an endorheic basin. And there are a few scattered around the world, but they're relatively rare and you shouldn't see them on every landscape. And it's really easy to create those sort of global features, which are incorrect and implausible if you're using an algorithmic procedural approach. Simulation. Because we're trying to mimic the natural processes of things like hydraulic erosion, models of individual tree growth, and these kinds of things, we're actually baking in the physical properties into the creation process. We tend to get pretty plausible results. As long as we parameterize these things, we set up the boundary conditions correctly, we're okay on this particular score. If you use a GPU to do this, and you do a local erosion operation, it can be efficient. But if it's too large scale, it's somewhat slow. But the problem is, as with all simulations, we have a controllability issue here. So the way you usually set up these simulations is you will create the boundary conditions, you'll specify the properties of it, and then you'll let it run. And then you'll see what the result is, and you'll adjust those. And that's not great for an artist. If you ask an artist to say, what's the erosion coefficient? Control this. Oh, it should be 5.2 and not 5.1. It's meaningless to them. They have to really spend a lot of time learning what those coefficients and parameters mean. So it's not great from an artist's perspective, generally. Okay. Then, maybe I should just move to me. Okay. Then the data-driven approach. And you might think that this would be the solution to all our problems. And it's pretty good, actually. We've seen particularly recently with some submissions to places like Pacific Graphics that you can do quite well with this. The idea is you take the existing data, and there's a lot of it, particularly for landscapes. So the entire world has been scanned at a 30-meter resolution. If you go to the United States, you can get it down to 1-meter resolution. You take that data, you feed it into something like a machine learning process, or perhaps texture synthesis, and you can get these kinds of results out. And nice, it's really nice, you can build sketching and painting interfaces on top of that. So it wins on controllability. It can be either interactive or real time, so it's okay on efficiency. Up until recently, we've had some issues with plausibility. So sometimes you get repeating artifacts. Sometimes it doesn't have those global properties we're looking for, like a lack of endoic basins. But I think it's really an evolving field, and this is quite a good way to go if you can. Of course, it relies on the data. So if you don't have the data to feed into the process, then you're stuck, really. And there are some domains where it's quite hard to get the data. So I'm thinking of things like cloud dynamics, getting the exact shape of clouds as they evolve over time in a local area is quite hard. Getting details of ecosystems. So getting all the tree positions on a 5 kilometer by 5 kilometer landscape. You just don't get that kind of data. So there are some flaws in this particular approach. Okay, so let me move on. I'm going to move on to show how we can try and achieve these 3 goals with a mix of the 3 techniques in 2 example cases. And the first one is a case study of the development of skyscapes. So this is in sort of weather simulation domain. And we want this because we'd like to convey things like the mood, what time of day it is, the season, and provide a sort of general atmosphere and feel to a scene. We'd like to simulate things like cloud, wind, rain, and sunlight, and ideally get these kinds of effects here. So this is photographs. This is not from an actual system, and we're not there yet. I mean, in particular, this kind of thing, where there's just incredible detail and variety in the kinds of clouds created. So there's lots of work to do here. This is sort of early steps in this direction. So what are the goals we'd like to achieve? We'd like to achieve what we call a deep representation. So that means going back to the physics and taking some of that and applying it into our system so that we get plausibility. We're looking to get a broad range of weather effects. So the whole gamut: clouds, wind, rain, snow, lightning, dew, fog, anything you can think of, we'd like to throw in there. In this particular paper, we only got through to clouds, really, and wind. Other ones less so. We'd like it to be interactive. So same goal as before. It's pretty hard to make this real time. So I think that's a reasonable goal. And then the scale of the virtual world should be what we call mesoscale. So this is something you'd see in a game, something that's about 10 kilometers by 10 kilometers in size. So that can encompass things like a small city, mountains, and so on. Okay. So I'm not going to go into the full details of the paper because that would be a presentation in its own right. What I'm going to do is highlight those things that I was looking at. So how have we combined the different techniques in order to create a system that works along the lines of the 3 goals? So here's an overview of the system. And this first part here is essentially simulation. So the front end is a simulation approach, and the back end of the system is a procedural method. And we use the procedural method to go from a coarse grain simulation in order to upsample it and to get more detail in sort of local areas. So it's an ideal combination of the 2 things. The dynamics of the behavior is physics-based, whereas the local detail is noise-based. A bit more detail about this. So these 2 halves are the underlying representation of the model and a little bit about the actual simulation. So one of the things about clouds, if you've looked at them for any length of time, is you'll notice they often are stratified. So there are some clouds, of course, that go up through multiple layers, but there are other clouds that actually appear in relatively thin bands, which means that quite a lot of the time you can represent clouds by taking sparsely scattered layers and setting them at the right altitude, which means that you turn a problem that would otherwise be very densely sampled in 3 dimensions into something that is relatively densely sampled in the horizontal, but sparsely sampled in the vertical. Realizing, of course, that the weather systems can span around 10 kilometers. I mean, the troposphere approximately goes up to 10 kilometers above the Earth, above the ground. So that's our representation. It's a set of layers, usually between 5 and 10, that we set at elevations of interest. And then within layers, we use advection. So this is getting onto the simulation side of things. So you store things like moisture and temperature and all the quantities you need for a weather system simulation within the layers, and then you just advect that. So that's wind blowing in from one side of the scene and transporting those quantities across. But you can't just do that with a weather system, because quite a lot of the interesting things in weather come from convection. So convection is that sort of uplift you get from heat sources on the ground. So we actually add a convection system to this to transport these quantities like temperature and moisture from one layer to the next. So once you've got the simulation working, and I'll talk a little bit more about the simulation later. Once you've got all that working, on this coarsely separated set of layers, you can use upsampling or amplification to improve it. And what we do there is we take the observation that the appearance of clouds is really dependent on two things. One is the amount of convection, and the other is the altitude at which it happens. So let's take, for example, a cumulus cloud. Cumulus cloud is basically, it's got that sort of boiling, bubbling appearance, mostly because of convective forces. So it's lifting the moisture of the cloud up and circulating it. Whereas a cirrus cloud, you know, that sort of a feathery horsetail effect, that's largely because of altitude. So if you take those two axes and you create a taxonomy based on those two quantities, you can create a specific noise function to do upsampling. And that's what we do at the back end of the process. Okay, so I've talked through most of this already, but this is just basically an illustration of the simulation. And of course, it has things like the need to change phases. So when your moisture reaches a certain quantity relative to the temperature, you're going to have humidity convert into moisture. And this whole process of doing this in stacks and doing advection, of course, is really well suited to the GPU. So that's how we speed up the simulation component to make it interactive. And then one really key thing about this is, and this, if you ever work in this field, by the way, my advice is to work with somebody who's an expert in the domain into which you're stepping. So if you're stepping across the line into botany, ask a botanist to come and help you. If you're working in weather systems, ask somebody who's an expert in that area, because they'll give you the key equations in physics. And it turns out that the key equation for dealing with convection is this moist static energy equilibrium, which talks about the situation under which parcels of air rise up or fall through the different levels. So once we had that, we could just apply it directly to do interlayer exchange. So here's an illustration of this. This is 3 layers, the lowest to highest. This is temperature. That's the advection. So we're using an RGB vector scheme to show the directions of the advection. And this is the important part here. This is an uplift layer. So this is the uplift between these 2 layers, and this is the uplift between those 2 layers, with red representing a convection upwards, blue representing convection downwards. And the important thing is to get what they call Rayleigh cells, which is a sort of circulating motion. And that was one of the things we looked for. So we looked to validate it by the appearance of typical behavior that you would get in the real world, this sort of convective motion. Weather systems have some interesting components to them. So apart from this fact that you get convection from heat causing the creation of cumulus clouds, you also get what are called orographic effects. which depend on the terrain. So the standard thing is you have kind of moist air. There's wind. It drives the moist air horizontally. It hits the slope of a mountain. Moist air gets pushed up the mountain. This is basic geography from school. It gets pushed up the mountain into a cooler band of air, and the moisture condenses. And you get clouds forming along the sides of mountains because of that. So that was one of the other things we had to include in our simulation. And you can see it happening here. There's some mountainous region in this area here. It's fairly flat over there. Moisture is coming from the left. And gradually you get these orographic cloud effects happening. I mean, I'm particularly keyed into this because I live in Cape Town in South Africa. And we have this massive mountain in the center of Cape Town. The city is actually built around the edge of the mountain. And it's called Table Mountain. And it gets a very specific kind of orographic effect, which we call the tablecloth because of Table Mountain. And you can see it here. So this is all orographic. It's because on the back of the mountain, moist air has been pushed up. It settles there as a cloud. And here it's boiling over the front side of the mountain. And it's hitting a warmer spot here. And so the moisture is being absorbed and the cloud is disappearing. And we want to make sure that we can simulate these kinds of effects, which are really key to good visual appearance in any kind of skyscape. I always like to show a picture of South African Table Mountain and Cape Town because I once got a postdoc from doing that. So it's I started off one of my talks by actually showing a picture, and he said, "Oh, I really like that, and I like to climb. So can I be a postdoc with you?" So if anybody's interested and if they like the look of Table Mountain and they like climbing, there's always a possibility. And then just to recapitulate the idea behind the procedural upsampling. So this is the second half that's a procedural mechanism, is this here. So if you take the classifications of clouds, things like the cirrostratus at high altitude with relatively low convection, you can put them into categories. So that's kind of the highest and least convective. And then on the far right extreme, of course, is the very interesting visual cumulonimbus, which spans a whole lot of altitudes, but has very high convectivity. So within a given cell of our simulation, we can say, what is the amount of convection that's there? What altitude is our layer at? And we can do procedural methods to create the actual individual appearance within the cell. So we go from something that's about 50 to 100 meters by 100 meters. That's the resolution of our simulation, down to a much, much finer resolution by procedural upsampling. Okay, let's talk about validation. So remember, I said that plausibility is a key thing here. So we look at some of the standard techniques for validation in the literature. So it's things like the formation of these convective cells, where if you heat the bottom, you sometimes see this in a pot of liquid, like a relatively viscous liquid. You heat the bottom in spots, you get this kind of bubbling, boiling, circular effect. That's called a Rayleigh cell. So we check for those. We check for diurnal cycles. So this is the day-night cycle in weather. Sometimes if you're on the seashore, you get wind coming in, and then when it goes from day to night, it'll go the other way. So we check to see that sort of thing was happening. And things like orographic effects, proper cumulo formation, mixed cloud forms, all of these things we checked for and made sure that they appeared in our simulations. Let me show you some of the results. I'm just going to go aside to this video here. Okay, so this here, it's not appearing. Okay, that's probably because I need to escape from that. Yeah. Okay, this is an example of multiple layers of different kinds of clouds appearing in a scene. So we've got some stratus clouds and low-level cumulus clouds, and you can see the kinds of layers happening over here. And then that's a top-level representation scene rendered from the ground. So that's a mix of cloud forms. This is an example of the orographic uplift effect. And it's basically those stills I showed you earlier. And you can see the sort of wispy clouds appearing in the mountain at the top. So they're going from left to right, basically gathering around where the mountains are. So that was a second form of validation. And then the next one I'm going to show you is basically the formation of cumulus clouds above an island. So the sea is a different temperature to the surrounding island. It's happening here. During the day, the island gets the sun, it reflects the heat, and you start getting convective forces happening above the island, creating cumulus clouds. So navigators often use this to explore and find land. They look for clouds that are typical above islands. Okay, so that just gives you a sort of sense of the kind of noise functions and things that can appear. Okay, I'll stop at that point. Right. Okay, so that's one example. And let me just do a quick evaluation of this according to the criteria that I was looking at. So this is a combination of a simulation and a procedural approach. Simulation first feeds into procedural upsampling, but there's nothing that's data-driven about this. So we don't look, for example, to see the thing from real data. We just look to see that the kinds of artifacts and effects that would appear in reality do appear. It is a combination of plausible, because of the validation, although what we didn't do is run user experiments of plausibility on it. And it's relatively efficient, but it is not controllable. So that's definitely a weakness here. It's not controllable in the sense that simulations are not controllable. So what you do is you set up the boundary conditions, you say wind's coming in from the left of the scene, it's got a certain random moisture in the particular layers, and that's how you design the scene. But you can't go into the middle of the thing and change it and artistically control it. So there's definitely room for improvement in this respect. Okay, let me show you one more example. Oh, and by the way, I should say that that previous paper, that was with the group that I work with at École Polytechnique. So Marie-Paul Cani and the team there. This next paper was with a PhD student of mine, Konrad Kapp, and with the team here. So this is me coming to the team here to tell them what they already know, but yeah. I think this is quite a nice paper from about 2 years ago. And this is data-driven ecosystems. So what we want to do here is we want to have an interface for artists to paint over forests of different densities and to control a distribution of species in those forests. And we'd like it to be large scale. So we're talking here 2 or 3 kilometers on the side. It's what I like to call the eco-placement problem. So we're not so much interested in the appearance of the individual trees. What we're interested in is where you place the trees and a little bit about their nature. So are they a very vigorous tree? What species are they? What height is the tree? All of those kinds of things. And then what you do is you hand over the results of that to a tree instantiator, something that will create the individual trees for you, like an L system or those kinds of things. So we'll assume that that part is all solved. What we just want to solve is where do you put the individual trees? Okay, and then as before, we want it to be plausible and interactive. Okay, I'm just going to show you the interface here quickly. So what the interface supports is 3 modes of density. So no trees, sparse trees, dense trees. And you can see, in fact, this is the sort of live example of the system in action. So we have brushes where you can paint on those kinds of densities. On the left is an offline rendering to show what the final results will look like. And when you paint a particular density, you get, I think I might actually go back so I can replay that. Yeah, so you can see it again. So when you paint a particular density, it creates a canopy, but it also tells you what trees of which species are appearing in that area. So that's the species map on the top left-hand side. And you can change the different portions. You can say, for example, I really want this to be a redwood-rich environment. And incidentally, we base this on data from the west coast of the United States, in particular an area called Sonoma County. And this is a fantastic offline rendering of an overview of the scene that was just created there with the different species. Okay, so that's the artist's view of the system. How do we get at that? We basically take every aspect of the tool set. So there's a combination here of data-driven in the early stages, procedural method in the middle, and then a simulation on the back end. So at the front, we generate canopy heights. So we have data from Sonoma County of what the heights of trees are on a pixelated grid. And we train on that data in order for people to be able to sketch dense, sparse, or empty regions of canopy. That just gives you basically the heights of the trees as an image. That's the front end. That's this stage here. So this is pix-to-pix standard machine learning approach with some modifications that were necessary to get it to actually work. Then what you want to do is you want to actually fit trees to that. So all we've got here is a field of heights. We don't actually have the individual trees. That's where we use the procedural method. So we use a kind of a spacing Voronoi diagram-like approach, which separates out the trees based on what the heights of the canopy is. So you put basically little spheres to represent the trees. You look at the visibility of a particular tree, and you move it to the centroid of its visible area. So if any of you have done mosaic techniques, we basically borrowed something that's 20 years old and applied it to get canopy spacing. And then the back end is fitting things like the undergrowth and the grass. So it's not sufficient to have this notion of what the canopy trees are. You want to put things underneath. And in order to do that, we actually do a simulation and take the data from the simulation and populate all the areas underneath. We have to do that because we don't have the data for under the trees. So we can't use this front-end data-driven approach to get the under canopy. So we have to use another method. So the first part is data-driven. The second part is procedural. And the third part is a simulation-based approach. And in essence, what we've done here is we've applied the right technique to the right part of the pipeline. So we're interested in making this overall thing as efficient as possible. These two parts are great. We get efficiency really nicely from those. This part is where we have problems. So a typical simulation over this kind of size of domain will take several hours. The way we get around that is we actually do an analysis of the results, extract some statistics from that, and then apply the statistics in real time. Okay, so a little bit more about each of these. So I think probably you mostly know about pix-to-pix and those CGAN techniques. So I won't go into too much detail about that. But what this is it's a mapping from the sparse brush-like data, which gets combined with the canopy height models. So canopy height model is an image of the heights of the trees. Nothing about the species, just what individual height is at a particular pixel. And we want to map using a CGAN from that to that. So you pair them up. You pair the brush representation with the canopy height model and you train on that. So that later in real time, the artist can combine those two things. Then we go from this representation. And notice, by the way, that even if something is dense, you'll have sparse areas inside it. And I should say, by the way, that also we use the elevation. So in fact, there's three channels here. There's elevation, there's the canopy height model, and there's this sketch map. So this is actually keyed to the elevation. There'll be areas where in real scenes, there's, for example, a river, there'll be no trees there. We'll learn that kind of thing even in the dense areas of the forest. And then this final step is where we do that bar noise spacing, where we fit specific species and sizes of trees to the data. And this is the back end. And so we've done the same kinds of things as we do with normal simulations. We assume that the trees are fixed, the canopy trees are fixed, and we create undergrowth beneath that. And then we validate it using growth curves from botany. So in botany, you have things like successor species taking over from some of the early ones. You need to make sure that the kinds of curves and behavior actually happens in our simulations. Then what we do is we take that data, we extract and analyze the distributions from it, and we apply it onto the landscape to get the final result. Okay, so we did quite a lot of validation of this, but this is just one example of validation. And I'll also talk a bit about the efficiency. So we took real data from Google Maps, and then we created another representation of it and rendered it in the same style, just to see that the same kinds of patterns appear. So this is from Sonoma County in California, and this is also a terrain, not the same one, not exactly the same one, but similar in sort of layout. And you'll see, for example, that on the west-facing slopes of both, you'll get fairly dense forests. So here, it's a west-facing slope, that's a west-facing slope. Similarly, this is a west-facing slope, and so is that. And you'll get the same sort of patterns of tree behavior, kind of fairly scattered, medium density, and the same one that appears there. So we're looking for the same kinds of patterns of tree density because that's what we're training for. And then this shows you some of the performance. So it's pretty good, actually, given how difficult the problem is, but really only interactive, I would say, and not real time, on something that's 1024 by 1024. So that's when you've got about 500,000 plants that you're developing, and there are different phases here. So that's placing trees on the canopy. This is doing the transfer of the undergrowth simulation. This is the total time over here. But we can scale up to something that's 3 kilometers by 3 kilometers with 5 million trees and get results in about a minute. Okay, so just to conclude, how does this one do? Actually does pretty well. I think we could still make it real time, but it's a nice combination of simulation, procedural methods, and data-driven. So data-driven on the front end, transitioning to procedural to place the canopy trees, and transitioning to a simulation to place the trees underneath canopy. And it does fairly well on plausibility, controllability, and efficiency, with perhaps a little bit of weakness in this regard. Okay, and then if you're interested, here are some papers in this domain. I think a lot of these are with this team. So this one, Eric, this one, and that one are all with the team. So about half of my papers are with this team. So as I said, I'm preaching to the converted a little bit here. But I think there's plenty still to do in this area. So it's really hard to achieve those 3 things I'm looking for. And very few of the current techniques actually do that. So I think there's at least a decade more research that's still possible in this area. Okay, folks, thank you for your attention. Any questions? Yes.
Thank you for your talk. I was wondering, to generate the trees themselves, you just have a template of trees, or you use some trees, or like how do you generate diversities and like depending on the species as well that you mentioned?
Yeah. So for that particular paper, they were set models, and there were a few selections of set models for each species. So it depends on the particular height, and then we would scale them to fit the dimensions. but it does sort of lead to some current research which we're working on at the moment. So obviously you want to have, if you have a particular height, a particular vigor for your tree, a particular canopy spacing, and maybe some history of the simulation, you'd like to make a very particular model based on that. And that's something we're working on at the moment. But it hasn't been published yet. It's really close to being submitted. Adrian has been sweating on that for what, 6 months now? Yeah, it's not easy because you have to do both the broad scale simulation, but also the individual trees as well. Yeah.
And another question as well. So you mentioned developing your models with domain experts, and then you mentioned like validating the model, the results with like the best people to validate them being hackers.
Yes.
Isn't it better to try to validate the model as well with experts?
That's the very best. So there's been a recent experiment where they compared people who had no expertise, hikers, and geomorphological experts. So that is people actually still working in geography and doing surveying and things like that. They were the very best, the geomorphological experts. The hikers were second, and the sort of run-of-the-mill people were third. The problem is getting those people and having them be willing to commit to your experiment. Yeah. So ideally we'd like them, but we don't always get them. Yeah. Yes.
We have a question about the thanks first. Thanks for the presentation. We have a question about the scaling stage of the cloud simulation. For now, you're using a LIRIS, is just fine enough for your experiments, but you mentioned being able to have data for that step. So yeah, maybe as a pure data, how to get to that.
Yeah.
Still, you can run very dense simulations and get that from as an output of the simulation.
Yeah. So
that makes sense in your pipeline, or would the effect be just very small at the end, the representation, and that much interest in investing time on that?
I think it actually would be a very interesting idea. I hadn't really thought of it. The way I would do this is maybe try and do some micro simulations offline, and then analyze those micro simulations and try and apply them. So within a particular cell, you know all of the quantities, you know things that are coming into it, you know what the temperature is and everything. You could maybe have basically a database of pre-analyzed micro simulations, get their statistics, and use that to do upsampling. That's, I think, an interesting idea, an interesting approach. We haven't explored that. Yeah. Thank you for the suggestion. Yeah.
I know, because it's reminded me of the fluid simulation papers where they try to, for smoke simulation or fluid dynamics, yeah. they simulate very coarse approximation of the geometry, and then they upscale that with deep stuff.
Yeah, yeah. Okay.
From data from previous very expensive simulation that they have read offline.
Yeah.
I don't know if that's...
Okay, I think I haven't encountered that paper, but yeah, I think you could definitely apply it. Yeah, interesting.
Actually, I have a question which just brought up.
Sure.
Sometimes real scenarios look unrealistic. You take that into account.
Yes, it's an interesting effect. It is actually why we don't like using normal run-of-the-mill people to do our experiments, because it's exactly for that reason. So if you take, for example, parts of California, some of the national parks there, like the Half Dome, for example, in that national park, looks deeply unrealistic, very interesting. We accept it because it's actually there, it's in the real world. If we were to put that into a digital scene, a person might say it's unrealistic. And that's why you want a geomorphologist or a hiker or somebody who's actually experienced with the full variety that you get in the real world, rather than somebody who's been trained on computer-generated things. Yeah, yeah. So it's a good question.
And I have just another one from the chat.
Sure.
So Mark Harpy is asking, he's saying that the results from the cloud simulation are incredible. In the rendering, it feels like there are three distinct heights for clouds, except for the cameras. Is it possible that the cloud morph from one height to another, so from one cloud type to another cloud type in the simulation?
We would have to prepare for that to happen in our simulation. It does happen in reality, of course, because you have evolving weather systems within a location. We'd have to put in a proxy layer for where the cloud was going to morph, even if it was relatively empty to start with. So this is one of the problems with the setup of simulations. You have to know what your eventual conditions are going to be at the end. So yes, we can do it, but you'd have to know beforehand that that was going to occur, and you'd have to spend the time designing for it.
Yeah.
Sure.
Do simulation have methods to avoid those bad things you were talking about? The one that when there's mountains that retain water, is there a way to take that into account into the model to avoid those bad things, or is that purely in a slide you show that when you are drawing mountains with the bad things, and that do simulation techniques avoid those bad things, or?
Sorry, I'm not sure the one thing you were asking. Do you say passing?
Basins, sorry.
Oh, basins. Oh, okay. Yeah, so none of these techniques here is about the geomorphology of the landscape. We've got lots of papers on that. We assume that for the clouds, you've got a set landscape. So we're not actually designing the landscape, it's a prior on the technique. So what would probably happen in that case is you might, if there's a bit of a basin there, you'd get the clouds coming over and settling into that basin area, the Enoic basin, and you might get sort of moisture developing there, which is what happens in real cases where you have a bit of a dip. Of course, what you can do is combine all of these techniques into one giant system, something that allows you to create the landscape and then put trees on it and then do the cloud system, but it's a very big system to do that. And we tend to work separately on the different components. So this was separate of the geomorphology. You just plug in a given terrain into the cloud system. Yeah.
One question for me.
Sure.
So it's from Clément Chomiki, who asks, using constraint-based methods like wave function collapse will have a place in this pipeline, and if so, at what scale?
Okay, which of the two systems, or just in general?
I would say it's general because it's my question, basically. I would say from a general point of view.
I hadn't thought of this. I don't know if any of my colleagues have an idea of whether it would be applicable or not. I'll throw this open to the floor.
I think it could be doable terrains in particular. I think that people already use that wave function collapse for generating environments, in particular in games. I mean, it's quite usual to have tiles and arrange tiles together using this wave function collapse system. And I think it has been used at least experimentally to generate terrains. I'm not aware of techniques like that for generating vegetation cover, such as forests. And I will not go deeper in that direction because this is ongoing work on my side.
Ah, okay. Yeah, so we won't reveal anymore.
But yeah, it's an interesting direction, and it's a way, in fact, to combine a tiling-based generation. And of course, we often like that because we work on a restricted subset of archetypes, and designers love that as well.
Yeah, because it leads to very rapid design cycles. You just basically are doing taking pieces and combining them and making sure that they line up along the edges.
Okay, let's meet and talk about that.
Sorry, it's recording now. So.
The question was not asked. Nobody remembers it.
No, but they will be delighted to discuss about that point with
Clément Chomiki.
Okay. Thank you.